That is a picture of planet Earth. It's a very nice image, isn't it? But does it rock you off your seats? Not really. Mind you, to our great-grandparents, this would have been a truly stunning sight. But for us, we've all seen something like this many times before, so I guess the novelty is worn off a little bit. But the reason I'm showing you this image anyway is because I think that it epitomizes what I believe to be an extremely important and at the same time totally underrated aspect of science, one that I want to emphasize in my talk today, and that is the ability of science to provide context. Now, it's sometimes claimed that all that science does is to merely describe the world around us. I think that statement is completely false. Science does a lot more than that, and in particular, it has enabled us to place every observation that we make, every phenomenon that we see, including ourselves, into a bigger picture. It provides us with context. Now, science does this in many, many different ways. For example, particle physics has taught us that physical reality is fundamentally reducible to just a few handfuls of elementary particles and 4 fundamental forces. In the same way, biology has allowed us to perceive that we humans aren't all that special as we once thought. We're simply one branch in the vast tree of life, connected in various degrees of kinship to all other living organisms. Now, returning to this picture, this actually shows us quite a lot that we cannot easily perceive otherwise. This picture emphasizes the fact that we live on a body, a planet of finite size. And moreover, that this planet can be viewed as a single, although quite complex, physical system. This picture reinforces the notion that global actions have global consequences and that ultimately the entire planet and everything on it share the same history and the same fate. Now, to my mind, that is absolutely central to what science does. Science not only tells us how stuff works, but by uncovering the relations between things, it provides us with context and thereby it broadens our horizons. Here's another image of planet Earth. Well, don't believe me? No, you're right, of course. This is Saturn as seen by the Cassini spacecraft looking back towards the sun. But the Earth is in this image. Here, let me show you. There it is. It's that tiny little speck of light that you can see there. So apart from all the great information, all the wonderful information about Saturn that is contained in this image, it also relays the realization that the Earth is simply a tiny little rock surrounded by a whole lot of cold and dark nothingness. So do you feel insignificant yet? No? Here, let me help you. Our solar system lives in a galaxy that is not entirely dissimilar to this one. Our sun is but one of approximately 300 billion stars, and it inhabits, in the words of the immortal Douglas Adams, the uncharted backwaters of the unfashionable end of the western spiral arm of this galaxy. So take this image. This is the deepest image of the universe ever produced by humankind. Almost every little fleck of light that you can see on this image is a galaxy that is billions of light years away. Now this image places us, our planet, our solar system, our whole galaxy into the context of an evolving universe that is 13.75 billion years old, give or take a couple of 100 million years. Now, from these examples, you will have gathered that the science of astronomy has had quite its share in providing us with high-level context in which to view ourselves. And the message that I want to get across to you today is that we are at the brink of making another giant leap forward in understanding our place in the cosmos. Now, central to the story is the telescope. Now, the telescope is, of course, the most important tool in astronomy, but I would argue that of all the scientific instruments ever invented by humankind, the telescope is right there at number 1 when it comes to broadening our horizons. Now, this is obviously true when, in terms of the literal meaning of broadening our horizons, but I think the case can also be argued for the metaphorical meaning. Now, this gentleman here is usually credited as being the first person to ever point a telescope at the night sky. This happened 402 years ago, back in 1609, and this is, of course, Galileo Galilei. Now, with his very modest telescope, he immediately made some discoveries that completely revolutionized what people thought they knew about the cosmos at that time. So, for example, his discovery that there are moons orbiting Jupiter refuted the whole idea that the Earth was the only center of motion in the universe. Now, time's moved on, and a lot has happened since then, and telescopes have come a very long way since then. And in particular, so here is today we have telescopes such as these, and this is called the Very Large Telescope in Chile. Very Large Telescope, rather prosaic name. Now, we astronomers are usually quite a creative bunch, but not necessarily when it comes to naming our telescopes. In any case, each one of these telescopes up there is 8.2 meters across, and that makes each one of them one of the largest telescopes that we have on the planet today. But together, these four represent the most powerful optical and infrared telescope system on the planet. But we've also branched out. Not only do we observe the universe in optical light, the light that we can see with our eyes, we actually observe it now across the entire electromagnetic spectrum, from gamma rays all the way up to radio waves. And this here is, as an example, is an array of 27 radio dishes in New Mexico in the US. And guess what this is called? The Very Large Array. We've also gone into space. Now, a lot of the radiation that we want to observe actually gets absorbed by our atmosphere, and it never makes it down to the ground. Or if it does, it gets blurred by the atmosphere, and I'll talk about that a little later. And so over years, we've put literally dozens of space telescopes, telescopes up into space, and this year, this guy over here is obviously the most famous one. That's the Hubble Space Telescope. Now, these are the kinds of things that astronomers have in their arsenal right now, today. But what I want to do now is to tell you about the future. Now, our vision of the future looks like this. This is a giant of a telescope, no less than 39 meters across. Now, I estimate this room to be about 20 to 25 meters across. So it's much, much bigger than this room. We will actually start building this telescope in just a few short months from now in the Atacama Desert in Chile. And this is called, wait for it, the European Extremely Large Telescope. Okay, when this thing is completed in about 10 years from now, it will be by far the largest optical and infrared telescope on the planet. And not just at that time, but for many, many decades to come. It will be the biggest eye on the sky. It will be able to collect about 13 times more light than the biggest telescopes that we have today. Now, what I want to do now is I want to tell you, just as a comparison for the size here, here it is in comparison to the Very Large Telescope I showed you earlier on, and in homage to Galileo Galilei, the Leaning Tower of Pisa over there. So what I want to do now is I want to tell you a little bit about the technology that we need to make a telescope like this work. So I told you that the main mirror of this telescope is 39 meters across. Now, 39 meters is far too large to make a mirror of that size from a single piece of glass. So instead, we're going to piece it together from individual segments that look like this. Well, they won't be made of cardboard and they won't be flopping around like this, but you get my meaning. So there'll be 1.4 meters across, and there will be 798 of these. And each one will have its own support structure that can move the segment around, it can tilt them, and it can even change the shape of these. And that's, of course, needed to ensure that all of the 800 segments together act as if they were part of just a single mirror of just exactly the right shape. Now, a structure of this size, you can't make this stiff enough to ensure that, or you can't make this stiff enough to stop it from deforming on its own gravity as the telescope moves across the sky. So what actually happens is that the telescope, by analyzing its own images, it keeps track of its own state. It kind of keeps an eye on itself, if you will. And it's constantly pushing and pulling all of its mirrors, not just the mirrors in the main mirror, but all of the mirrors in the telescope. It's constantly pushing and pulling them about once every second to make sure that the telescope as a whole delivers the best possible image quality at all times. So being able to segment your mirror, being able to actively control your telescope like this is absolutely crucial to making a complex machine like this work. But there is more. And one of the reasons why astronomers want to build bigger and bigger telescopes is because the sharpness of an image, the level of detail that you can see in an image, depends on the size of the telescope. The bigger the telescope, the sharper the image. Now that's true in principle, but in practice there's a hitch, and that is the atmosphere. And when you stand out in your backyard or on the street at night and you look at the stars, you can see the stars twinkle, right? You've all seen that, right? Now, the twinkling has nothing to do with the stars. Stars don't twinkle. The twinkling is caused by turbulence in the Earth's atmosphere, by different pockets of gas, of air, having different temperatures and different pressures. Now, the twinkling looks quite pretty, doesn't it? And at times it's even quite romantic. But for us astronomers, it's a real pain in the neck. because it distorts our images. It blurs them. It makes them less sharp than they could be if it wasn't for the atmosphere. In fact, with the pretty big telescopes that we have today already, it is the blurring caused by the atmosphere that limits the sharpness of the images and not the size of our telescopes. But if that's true, what's the point of building even bigger telescopes? Well, the reason is because we can do something about it. So let me try and show you here. So here's a telescope looking at a star, and as the light waves from the star traverse the atmosphere, they get all distorted, and that causes this blurry image over there that's dancing around. Now, you can get a computer to analyze this signal, and then the computer sends back a command. Can you stop it there? Sends back a command to a particular mirror in the telescope. And now, initially, this mirror is flat. So all the distorted light waves that are coming in remain distorted after the reflection of this mirror. But then the mirror receives a command from the computer. Can you stop there? And if you look very closely, you can see that the mirror is very slightly deformed itself. And deformed itself in exactly the right way in order to cancel out the distortions so that after the reflection, you get perfectly straight light waves coming off the mirror now. And that is what produces then super sharp and super stable images, as you can see up there. Now, this whole process of detecting the distortions and deforming a mirror happens in real time while the observations are going on, and it happens about 1,000 times per second. Okay, so this is really going on in real time. So effectively, what we're doing with this technique is we're untwinkling the stars. So that's pretty cool. But for this correction process to work, we need a very bright star in the sky for the telescope and the computer to lock onto it. But that's a problem, because very bright stars are actually very few and far between on the sky. So what if I'm interested in some object that doesn't have a bright star next to it? What do I do now? Can't I use this technique? Well, the answer is I can make my own star. Now, this image looks a little photoshopped. But it's not, I promise. This is a real photograph. And what it shows you is a telescope firing a laser at the center of the Milky Way. Well, actually, of course, the laser doesn't make it that far. The laser beam only makes it up to an altitude of about 90 kilometers, where a layer of sodium atoms absorbs the energy of the laser beam and starts to glow. Now, from the ground, this glow looks like a star. And we can use this artificial star for the telescope and the computer to lock onto. In fact, in the new telescope, we'll be using multiple laser stars because that makes the whole atmospheric correction process even better. So wonderful. We can now make images from the ground as if the atmosphere wasn't even there. Problem solved. Except that once in a while, somebody seems to get all angry at us for poking around in the sky with a laser. But never mind. So these technologies that I've been telling you about, they've been developed by very many very smart people over the past 20 to 30 years already. So none of this stuff is actually particularly new. A lot of this is already being employed in existing telescopes. But in the European Extremely Large Telescope, we're really going to take this all to a new level of complexity. And while at the same time, because we have all this experience with these techniques, we can be quite confident that we can actually make this work. Okay, enough said about the technology. You can wake up again. Let's talk about some science now. So this telescope is not being built to answer a single scientific question. Instead, it will address a whole range of topics in astrophysics, from our own solar system to stars, from nearby galaxy to the most distant objects in the visible universe, from fundamental physics and cosmology. It's all there, you name it. But one thing that I find particularly interesting and that I want to highlight now is the topic of extrasolar planets. An extrasolar planet is a planet that orbits another star, just like the planets in our own solar system orbit the sun. Now, over the past 16 years, we've discovered several hundreds of these extrasolar planets. But this is a very difficult thing to do. And for the most part, we've had to rely on very indirect methods. What do I mean by that? Let me show you. So here's a planet orbiting a star, and because of its gravitational pull, it actually makes the star wobble ever so slightly. It's exaggerated here in this movie, but the star wobbles. And we can see this wobble in the spectrum of the star. The spectrum is where we take the light from the star and spread it out into its constituent colors. And in this spectrum, we can see these dark absorption lines, and we can see them periodically moving towards lower and then shorter wavelengths, reflecting the wobble of the star. Alternatively, if we're lucky enough, and if the orbit of the planet is exactly aligned with our line of sight to that system, then we can infer the presence of the planet from the fact that the brightness of the star is dimmed ever so slightly. Why isn't this playing? I mean, it doesn't matter. It's dimmed ever so slightly as the planet passes in front of the star as seen from our viewpoint. Now, in both of these methods, we never actually get to see the planet. We only infer its existence from its effect on its parent star. But we want to see the planet. Why? Well, here's the key. We want to see the planet because we want to be able to study it in enough detail to see whether it harbors life. And by life, I don't mean little green men, right? Any kind of life will do, thank you very much. But how can we possibly do this? These things, these systems are much too far away for us to be able to send a space probe there. So how can we do this? Well, if we can see a planet, then we can also take a spectrum of it, meaning a spectrum of its atmosphere. If I can take a spectrum of an atmosphere, I can tell quite a lot about its chemical composition. And that's because the different elements and molecules all leave a very characteristic signature in the spectrum. It's these wiggly lines there. It's almost like a fingerprint. So on Earth, we know that the emergence of life significantly changed the chemical composition of the Earth's atmosphere. So if we were able to detect the presence of, for example, oxygen and methane in the atmosphere of an extrasolar planet, then this would be pretty good indication, a pretty good indication of life on that planet. Now we can, in some very rare cases, we can already see extrasolar planets. Here is the first such image of an extrasolar planet. It's that red dot over there. The other thing is, of course, its parent star. Now, this planet is about 5 times the mass of Jupiter, and its distance to the host star is about 1.5 times the distance between the Sun and Pluto. Now, this is not a promising place to go looking for life. Why? Because it's far too cold out there. We think that for the development of life, you need liquid water. And out there, you just ain't going to find liquid water. It's just not there. It's too cold. So the best place to look for life is on a planet that is much, much closer into the star, that lives in what we call the habitable zone. Now, the habitable zone is simply that zone around a star that is at just the right distance so that a planet in that zone receives just the right amount of heat to keep water liquid. So it's not too far out where it's too cold, and it's not too far in where it's too hot. So not surprisingly, the Earth is in the Sun's habitable zone. Now, where exactly this zone is located depends on the details of the star, but in general, it is always true that this habitable zone is very, very close to the star, and that is a huge problem. To see why, imagine that we get on a spaceship and that we fly out into interstellar space. And after about say 30 light years, we turn around and we look back at the Earth. What are we going to see? Well, from this distance, the Earth is going to be really, really close to the Sun. Now remember, the Earth itself does not shine. It only reflects the light from the Sun. So it's very faint by comparison. So what we have here is we have something that's very, very faint, extremely close to something that is very, very bright, namely the Sun. Can you see why that is a problem? So this example of seeing the Sun-Earth from a distance of 30 light years is akin to taking a tiny little LED, placing it next to a stadium floodlight, only about 10 centimeters away, and then trying to see that LED in the glare of the floodlight from a distance of 200 kilometers. Okay, that's about the distance from here to the Black Sea coast. Okay, this is very hard to do. And this is the reason why we need super sharp images, which you can only obtain from a giant telescope that is equipped with deformable mirrors and all that other great stuff I was telling you about earlier. Now, we think that with the European Extremely Large Telescope, we will be able to directly image and perhaps study in more detail possible life-bearing planets within a distance of about 25 light years from Earth. Now, with a little bit of luck, that may provide us with our very first glimpse of extraterrestrial life. So, with this new telescope, my science, the science of astronomy, is experiencing the dawn of a new era. One that will bring new understanding for our place in the cosmos. One that has the potential to really revolutionize our perception of life in the universe. Right now, we know of, for certain, only of a single place in the entire universe that harbors life. This is it. Let's change that, shall we? Thank you.